Hello, good afternoon. So my name is Enrico. I work at Vale, and today I'll be talking about some impact estimation on the mining industry that we have performed here. So first of all, a little bit more about Vale. So Vale, our business is actually related to mining. We are among the world's largest producers of iron ore and nickel. And we are also a major copper producer, and we also have gold, silver, and cobalt operations. And our operations, they range from the mining, processing, and we include all of the logistics. So we are also have very strong operations on railways, ports, and terminals. Here it's just to give an example about how much we are spread around the world. So currently we have operations or offices in 18 different countries in almost all continents. And then as you can see, there's really a very large and very spread operations all over the world. And I'm part of a team that's responsible for simulation. So we have an operations research team that does operations and help new projects as well as improvement of existing operations. So here this is the table of contents. So I'll start by describing briefly the two problems that we are going to be presenting today. Then I'm going into why we picked AnyLogic for the tool to solve this problem. And then on each one of the two problems, I will go into the definition, data gathering, modeling, and the results that we have achieved. Okay, so we will be dealing with two problems. The first problem can be seen here on the left. It's a problem on one iron ore mine, which is part of the S11D project. This is one of the biggest projects in the history of iron ore mining. And the idea here is to increase the capacity of waste crushing. So we try to propose a new operational model. However, this operational model, defined here in green, it's actually going to have influence on existing operations of small road vehicles, here described in yellow. So the idea here is to estimate the impact that this joined operation would have one on another. And the second problem we will be talking today, it's we already have a very extensive logistic network. And in order to increase the usage of our logistic networks, there was a demand to evaluate additional train loading at a rail loop in order to provide more ore to be transported by the trains. This new operation, it would load material on the trains, but the arrival of the material on the stockyard, it's a different origin than the currently existing operations. And expanding the current road, which is very narrow, into a two-way road would require extensive earthworks. And we would like to assess what's the impact of not extending this road. So first of all, why AnyLogic? We decided for AnyLogic, it's actually a discrete event simulation software package. We found it really useful to use some of the existing libraries. So we are very used to use the bulk product handling road traffic process modeling libraries. It's also nice that it has geographical information systems integration. In our case specifically, we have a lot of usage for this in the mining industry. And finally, we find it that the agent-based modeling, it creates an ecosystem where it's easy for us internally to make extension of the existing libraries or of new libraries. So it should allow us to be faster in developing new models as long as we can actually use agents from previous libraries that we have developed. And this is actually the last point. So we can actually reuse several different agents in several different cases. The problems here, actually, we are going to be presenting a couple of agents based on the road modeling library that we have developed internally for one project and how we actually used it to bootstrap a second simulation model. So now I'll be talking about the first problem. So the first problem, it's in the interaction between haul trucking and small vehicles. Just giving a general overview, S11D, like I said before, it's one of the biggest projects in the history of iron ore mining in the whole world. The idea of this mine, it operates with in-pit conveyor crushing and also a little bit of trucking on a mixed model. And usually open pit mines, we have two materials that have to be hauled. These materials, they are run of mine and waste, and the run of mine, it's fed to the processing plants in order to become the product. And waste material, it must be removed and has to be dumped on waste piles. We have here the current status of the mine of S11D. The region of interest to be studied on the project, it's actually this square here. Right here, we have a waste crushing structure that we wanted to evaluate the expansion. And right here, we have one conveyor that takes the run of mine to the processing plant. We have one conveyor that takes the waste to the waste pile. And we have one road access here that leads either to the waste pile, but also road to external areas to bring operators and other personnel. So bringing in more detail here, in this area, we were trying to study increasing the number of crushers. However, in order to increase the number of crushers here, we would have a kind of traffic that's not safe to be joined together. We would have the hauling trucks coming on the green line, and we would have the yellow current road traffic existing. However, the simultaneous track of these two kind of vehicles, it's forbidden. We can see here just a picture for scale. So the hauling trucks, they are really huge compared to normal vehicles, to the point that the operator cannot even see the small vehicles. So in order to operate on mixed traffic here, we would like to provide automatic road gate barriers so we could stop the road traffic whenever there was a haul truck performing its dumping here on this area. In order to gather the data from traffic, the traffic that's on that yellow road, it's actually composed of buses, small car, road trucks that transport people, waste, and materials. All the vehicles entering or leaving the mine, they are tracked due to the access control. So there's also a gate barrier on the entrance of the mine. So we know which vehicles are entering or leaving the mine. We also know all of the vehicles transporting waste. We are tracking them for production purposes, but there is still some traffic that's related to internal movement of people or other internal movement of materials that does not get tracked directly. So we went on several hours of the day and performed field track data collection in order to evaluate how our tracked and our untracked traffic relates. And then this traffic, it was actually converted into a scheduled rate for the model. The scheduled rate for the model was actually the observed track rate added with around at around 10% increase in order to evaluate for the difference between the tracked flow and the total flow of vehicles that we have observed. As we can see here, there are a couple of periods that have very different traffic profiles during the day. So up until the morning, we can see that there's very low demand for our traffic. And then it actually increases quite a bit. And during lunchtime, there's actually need to shift the operators to perform their meals. And then there's an increased road traffic. Then we are back to the daily baseline. And then we are back to the night baseline, which is really low. And we also noticed that there was a difference between the traffic flow during the weekdays and the weekends. So actually we modeled this as a scheduled rate in any logic, considering all of this possible variation here. So here is a quick screenshot of the model. In this model here, we developed an agent to manage this kind of restricted or interference areas. And this agent is capable of controlling all entrances and exits of vehicles on its controlled area. It was tried to be later extensible. So the entrance is controlled by setting the traffic light on each one of the stop lines before entering the restricted areas. In this case here, this is the entrance of the restricted area for the hauling trucks, and these two are the entrances for the small vehicle traffic. There's also one additional agent that comprises a parking lot with delay for the unloading with control of empty positions. So if you try to move to a parking lot that has all of these spots already used, AnyLogic actually, the cars will not queue on the street. The cars will throw an error. Then we have also developed one internal agent here that is part of our library that it can perform, the car moves right before the parking lot. And if there's not enough spaces, it actually just sits on the road until there's enough space. And the arrival of both haul trucks and small vehicles is defined by schedules. And this is the area that we have interested in doing the study. So here we can see a couple of videos. Here we can see, for example, small vehicles closing the road gate barrier for the hauling truck. And whenever there comes a hauling truck, it has preferences, so it closes the road for the small vehicles first. And then until it performs its operation and it leaves the area, the road traffic accumulates here. On the other side, there's also a video that we can see here, and this is regarding the parking lot. So the operation of the parking lot on AnyLogic, usually the third truck here, there's not enough space, so it just sits in a queue. And our agent is able to collect all kinds of statistics regarding the queuing times, the queue sizes, and everything else that you would expect of such an agent. Here are some results. So the traffic was simulated during 1 week. We used a 10 replication, and we also evaluated different models of hauling trucks. So trucks with higher capacity, they lead to less trips needed in order to achieve the target total transport tonnage. And less trips also lead to less time blocking the road traffic. And in order to estimate the maximum capacity of the gate barrier, we also ran some scenarios with double the required traffic in order to assess how everything goes here. Then we can see here on this chart on green, the number of hauling trucks per hour. Actually, we just do not have the axis here because these numbers, I cannot bring them here. But the road traffic vehicles, then we can also see their numbers here. So when we talk about the lower payload trucks and the higher payload trucks, it's visible on the green lines that the higher payload trucks, they actually lead to much lower number of trips. So the number of trucks per hour is much smaller. And we can also see that in both cases, the current road traffic, which is in yellow here, it can be accommodated, so there was no bottleneck identified. And once we double the demand, actually the lower payload truck, it could achieve around 645 vehicles per hour on peak, and the higher payload could achieve 669. There's also some stop of the hauling trucks here, and it's due to operator change of shifts. So there are 2 hours where we won't be operating. It's the final cycles for the shift that is leaving and moving to the points where we can actually change the operators. And there's also 2 stops, one during the night and one during the day, in order for the operations, for the operators to have their meals. After this, we decided to study in more detail for the scenario with the for both scenarios, how does the gate barrier work on open and closed times. And here we can see on the lower payload on gray, the curve is always below the percentage time of open of the higher payload. So this is the percentage that it's open for road traffic. And then we have a quick table here. When we are talking about lower payload trucks, the barrier stays open for around 73% of the time, and for the higher payload truck, 83%. And the average open and average closed times and maximum closed times are also seen here. But most important, it was really interesting that we gained around 50% open time on the average open time. So this reduced the chance that road traffic would encounter some blockage. And thus, we decided to proceed with the higher payload trucks for this project. And then we also performed a study of the queue and traffic analysis for the road vehicles only for the higher payload scenario. So on the current traffic that we are estimating for the road, around 18% of all road vehicles have some kind of impact, either due to congestion or due to the road gate barrier being closed. And when they are impacted, they are stopping or losing around 2.45 minutes of trip time. Once we increase our traffic up to 20 or 40%, we can see that the amount of vehicles being impacted due to traffic or gate barrier, it increases by a substantial amount, especially on the current traffic plus 40%. And then the impact can go up to 2.66 minutes when there is an impact, but the impact goes from 18 to 23%. So with this, I close the first problem that we are going to be showcasing here. The second, it's going to be a wait station capacity. This is somewhat similar to one project already discussed here today. But in order to increase the usage of the existing logistic network, we have to evaluate how we can load more train volume through this rail loop here in Serra Leste. This new operation marked in green, it would work on a road different than the existing operations. The existing operations, we bring material to this rail loop only on this yellow road here. However, we can see from this cut here, we would require extensive earthworks, because this here, it's really narrow. There's just the railway and a one-way road. We have one entrance here with a weight bridge. However, it sits inside this restricted area. And with this new operation, we will have a very big increase in the green area traffic. And then we need to assess the capacity of the current structure. And as this new operation increases, we also wanted to evaluate the maximum capacities by having new weight bridges on a new location and either 1 and 2 weight bridges. So here we have some sample of the modeling. Again, we are using the road library. There are 4 simultaneous dumping positions. The restricted area, it's actually controlled by the agent that we developed on the previous project. Every inbound truck must be weighted. It comes in loaded, and whenever it's outbound, it also has to be weighted for the tear. However, if additional capacity is required, we can sometimes use previous tar from the truck if it was recent enough. So in this case, we can actually gain a little bit of capacity depending on how long do we estimate that we can still use the last empty waiting from the truck, since this is all just internal traffic. We have here some models. So we can actually see that with the existing weight bridge inside the area, the capacity is very limited. We can see the trucks actually waiting entrance here. And then we have here one scenario on the new weight bridges with 2 weight bridges. We evaluated 1 and 2 on the new position. And then in this case here, actually the trucks are trying to go on the weight bridges, staying outside of the restricted area. So the restricted area could be a little bit more productive. So we run here for each of the three scenarios, existing weight bridge inside of the restricted areas and 1 and 2 weight bridges outside of the restricted areas. We also did a sensitivity analysis to the arrival rate of trucks. So we have 9 levels of different arrival rate of trucks. And also we are using 5 different levels of required empty truck there waiting. And again, the worst case, which is the current scenario, it's considered 100% of unloading capacity. So here we can see some of the comparisons between the different scenarios. And some results that were considered interesting for us is, first of all, reducing the empty waiting from 100% to 200%. It actually shows a very small increase of capacity on the waiting bridge. So we went from 100 to 130% capacity. And this signals to us that the bottleneck is not just on the waiting bridge, but also on the restricted areas. We can see on two here. So if we just move the waiting bridge to outside of the restricted area with 100% empty truck waiting, again, we don't see barely any improvement. We go from 100 to 106% capacity. So this is showing at this point that the weight bridge is the main bottleneck in this stage, because this is already outside of the restricted area. And when we go into 20% empty truck waiting, then we have the third finding, which is quite interesting. So for one weight bridge outside of the restricted area, if I can relax the constraint of empty truck there waiting, we can actually gain 70% capacity with just one weight bridge, which is very close to the amount we would get with 2 weight bridges outside of the restricted area. When we see here, outside of the restricted area, 2 weight bridges, the weight bridge is no longer a bottleneck, so we can almost double the capacity. However, for 20% empty waiting, the weight bridges, they were already not a bottleneck, so there's very small improvement. And then in the end, this project here, we evaluated the capacity, and this was used to make the decision on how many weight bridges to purchase and where to place them over time. Okay, so I have finished the presentation. Let me just open the questions and answers here. Okay, so the first question here, I'm interested in understanding if you have any solutions or implemented case studies in manufacturing factory floor simulation. Jeffrey is going to be answering this one, but right now we are mostly on bulk material. So we are a mining company. Even our processing plants, they are more related to bulk material plants. So we are talking more like crushing, flotation, milling, and operations like this.